אז שלום לכולם וברוכים הבאים. למי שהגיע מכל מיני לינקים ממקומות מוזרים, אנחנו מועדון הקריאה של NLP. שמתי בצ'אט עכשיו לינק להזמנה לוואטסאפ שלנו. בקבוצת הוואטסאפ תוכלו לראות הזמנות לכל אירועים. וכבר אנחנו יודעים על האירוע הבא שלנו, שהוא אירוע יוצא דופן. ביום שלישי בשבוע הבא, אנחנו נקיים אירוע משותף יחד עם מדס, קבוצת Medical Data Science ישראל, בנושא של Chat GPT ו-Healthcare, כל הבאזוורדס ביחד, עידן. זה יהיה יותר דיון ופחות הרצאה, אז מוזמנים להצטרף. זהו, ומזל טוב לשני. ואני אציג את הדובר שלנו היום. אז היום ידבר יונתן ביטון, שהוא דוקטורנט באוניברסיטה העברית, אצל גבי סטנובסקי ורועי שוורץ, ובמקביל הוא גם חוקר בגוגל, והוא ידבר איתנו על תחום שאנחנו פחות מדברים עליו בדרך כלל במועדון, אבל שאותי אישית מאוד מעניין, וכנראה עוד הרבה אנשים, שזה שילוב בין ויז'ן לשפה, וספציפית ריזונינג על תמונות. וליזה, אני לא יודעת מה איתכם, ליזה, נורא כיף לגלות דברים שכל ה-Chat GPTים עוד לא עושים כל כך טוב, אז רק על זה מגיע לך להרצות פה. וזהו נראה לי, בהצלחה יונתן.
טוב, אז שלום לכולם, תודה רבה שבאתם. אז באמת אני באוניברסיטה העברית, דוקטורנט, בהנחיה של גבריאל סטנובסקי ורועי שוורץ. אני אעביר את ההרצאה באנגלית, כאילו אתם יכולים לשאול שאלות בעברית או באנגלית, וכמובן אני אשמח לפידבקים גם תוך כדי, וכאילו מוזמנים להשתתף ולשאול וגם אחרי. זה גם הרצאה שאני אעביר בעוד אוניברסיטאות בארץ, אז כל פידבק יהיה מעולה. Okay, so why vision and language? There are multiple real-world problems that can benefit from a good vision and language models. For example, medical visual question answering, where doctors can look on, for example, X-ray images and ask questions and receive automatic responses. And additionally, helping visually impaired people. For example, this image is from a dataset called VisWiz, or there is some application you might know that is called Be My Eyes, where like blind people can use their mobile phone and to ask people, can you please tell me what this scan is? And one of the premises or goals of artificial intelligence is to have agents that we can communicate in natural language, and the agents can perceive the environment and perform actions in the real world. And actually now it is more easier to convince about real-world applications. And we have examples like from Twitter with GPT-4, where someone can take an image of the fridge and ask GPT to generate food recipes from the ingredients in the fridge, or to take a photo of a website that was drawn with pen and paper, and it can transfer like to a real website. So these are all nice applications. Now, recognition and images like and datasets like ImageNet and MS Coco is not the main bottleneck nowadays. It was like difficult tasks like few years ago, but since then the community have done great progress, and with these datasets we reached where we are today, which is a great place. But this is not the main bottleneck right now. And to convince you why, I want to ask you what makes these images weird. Like take a second and try like to look on this image and say what makes it weird. Do someone have a guess on what is weird in this image?
The right image has the thing that should be on the dog. The man.
Yeah.
It's carrots instead of cucumbers.
Yeah.
And
Yeah.
Bill Gates wouldn't be caught dead with an Apple computer.
Yeah. Okay. Yeah, you got all of this correctly. But why should it be cucumbers and not carrots?
Because it's a common face mask treatment that it has carrots.
Yeah, and like it actually like have like it related to moisture, that like it can reduce sourness in the eyes. I didn't know this as well before like making this image, but yeah, all of the reasons are grounded in some real world fact or knowledge or common sense, and yeah, so. We believe that AI needs to be grounded in the real world to achieve true common sense reasoning. And these images are from Whoops, which I will discuss, like present and elaborate in this talk, but I will cover like many other works as well. But we will get to these images in few slides again and this work. But like the point of this slide is to like convince that we need reasoning beyond recognition. And that's what this talk focuses on. Okay, so my research agenda, which is a personal premise, is that building successful AI systems in the upcoming years will largely depend on the availability of high-quality data sets that represent challenging tasks, rather than improving modeling techniques. I'm not saying that modeling is not important, but I am saying like I believe that data sets could be like another source of improvement on challenging tasks. And there is a growing body of research that supports this premise. And one notable example is Instruct GPT, where OpenAI took GPT-3 and added 100,000 samples of instruction tuning, and they took the same architecture, like the exact same architecture, and just fine-tuned it on like not too much samples, and it caused like a major improvement. And like Instruct GPT is one of the models that behind the advancements that led to ChatGPT. So it was like a significant advancement in the field. So my methodology for advancing this agenda is one, to push the boundaries of vision and language with challenging data sets. And it resulted in publications in NACL 21, URIP 22, and AAAI 23. And then to improve model generalization, which includes publications in EMNLP 21, ICCV 23 submissions, and more. And executing this methodology, I try to construct creative tasks and to employ tailor-made solutions that we will see like in the next slides. And it includes leveraging rich semantic inputs. For example, we will see works that leverage scene graphs and leverage visual SRL, semantic role labeling data sets, and making contrastive perturbation and cross-model analysis, crowdsourcing, smart filtering, gamifications, recruiting experts, and finally, utilizing models, which are LLMs and text-to-image models as well. Okay, so far, okay, let's, I just looked in the comments 1 second. Okay, so let's talk about the first like track of pushing the boundaries of vision and language with challenging data sets. Okay, so in this work, this is automatic generation of content sets from scene graphs presented in NACL 21. We leverage scene graphs, which are graph representation of an image. And it represents like the objects and their attributes. For example, that the fence is made of wood, and also the relationships between the objects, like that the zebra is behind the fence. And we started from like a simple VQA instances, like is there a fence near the puddle, with an expected answer of yes. And using the scene graph, we just made like edits to create augmented questions. So we created the following augmentations. Is there a wall near the puddle, or is there an elephant near the puddle? And now the expected answers are changed to no. So this is, and we then show that models struggle on these contrasets. And if we fine-tune models and activate like this perturbation also on the train set, and like augmenting the train set and adding new data, it will result in more robust models that achieve better results on this type of like challenging questions, or not really challenging, but different, like out of distribution. And another track, like major track in the research, is common sense benchmarks. And there have been many common sense benchmarks proposed over the years in like NLP, classic NLP. And models seem to approach human performance, but not always from the right reasons. And the question is, can vision and language models handle common sense tasks? And how to create more challenging and less saturable benchmarks? It means that benchmarks that, like in NLP, there have been benchmarks challenging, but with time it became much easier. And here we asked ourselves, how can we make it like more challenging, but also like to maintain maintain the challenge throughout time. And we developed several benchmarks to test it. And the first is VASR, Visual Analogies of Situation Recognition. And it was presented in III 23. And here we have an analogy. So we have A and A prime, and we have B, and we need to search or to select the B prime, which is the image that is most similar to B, the same way that A prime is similar to A. And actually, like one question before is that, like, we all know word-to-vec analogies. So we have man to woman is like king to queen. So this is the same thing, but with images. So if this is the man to woman and this is queen, and now we need to find like the image, to select the image that best completes the analogy. So do someone have an answer for what candidate best completes the analogy in this case?
One.
Yeah.
Three.
Three.
Yeah.
3. Okay, yeah, correct. This is actually 3, because here we had a man swinging on a tree, and here we have like a monkey or an ape swinging on a tree, and here we have a man shivering in the cold. So here we should have some kind of a monkey shivering in the cold, and yeah, the answer is 3. So like, yeah, this is not very easy, and this is the point to challenge models. And to solve this, we need to understand what is the key difference between A and A prime, and then to map this difference to B. So, okay, so this is one work.
Can I ask a question about the picture you just shown?
Yeah.
So with words, the analogy is much clearer what you're looking for, but here I didn't know the answer because I was confused by A prime, because it kind of shows 2 monkeys, and I didn't know if I'm supposed to turn one man into 2 monkeys or something. So it's not written on the face of it what the change is. You need to deduce it using pragmatics and a prior on the probabilities of the world. So it doesn't seem exactly the same. Maybe you have something to say about it?
Yeah, this is completely true, and we acknowledge this ambiguity. And in fact, when creating dataset, we actually leverage another dataset. We leverage a visual semantic role labeling. So if you're familiar with SRL in NLP, so we have a sentence and we have like the agent that performs something, and we have the verb that is the activity that is being like the activity in the scene. So we leverage this kind of semantic but to create the test set, we used a human annotator. So we had 5 human annotators, and we selected the majority vote as the final answer. So our way to like resolve this ambiguity is just to take what most of the humans were thinking about. And yeah, so this is correct that an additional change is that there is one like man, and here there are two apes. So it might be that the main difference is 1 to 2, but we don't see anything with like two objects here. And if there were two objects, this example would be ambiguous, and it would probably will not reach an agreement among the human annotators. But yeah, this is a great point.
So maybe here it can be solved more easily by the algorithm if the algorithm first translates the visuals into words.
Yeah,
It might
yeah, this is
help it.
yeah, this
But
is
isn't the ambiguity there like inherently? Humans don't.
Yeah, it would be man to two apes, like shivering man to what? But still, I really agree with Aviv. Maybe it's because we're all NLP people, but like in words, it would be a lot easier for me.
yeah, like one of the methods were to use image caption models to translate each image into like a sentence to describe what happens, and then to try and solve it with like SBERT and method. And actually the results, they are fine, but this is still very challenging. And the results are lower than the visual models as well. And in few slides, we will show how we solve it with models, but this data set is still like the best results were about 55%. So it is still challenging. Okay, so this is another work, Winogavir, and it was presented in Europe 22. And in this case, do you know the game Codenames? I assume that some of you know the game Codenames. So we have, this is like Codenames with images. So we have a queue, werewolf, and we need to select like the top 2 images that best associate with the queue. And here the images are the photo of a puppy and the photo of a moon. So this is like a fun instance, but the actual fun way is how this instance was created. So we made an online game where we have a spy master, Alice, and her task is to create a queue that will both challenge and fool an AI model in the loop, and both will be solvable by 3 other human solvers. So we had like Amazon Mechanical Turk workers that played the game, and they received actual money and bonus for satisfying these 2 conditions. And they received like really nice bonuses if they both managed to fool the model and to make it solvable by the humans. Like the bonus was really like correlated with the joint like performance on both of these conditions. And this game is like this benchmark is considered as a dynamic benchmark. So it means that people can still play it, and when they play it, here we had the clip model in the loop, which solves the results, and the clip model was pretty good. So the people tried really hard like to make to fool the model, and they had to come up with very creative cues in order to receive the good payment and the bonuses. And the nice thing is that we can update the model all of the time, and to make it like a stronger model, and then like to keep updating the benchmark with new instances. So this is the Winogavir work. And another work, this was published pretty recently by Ron Yosef, which is a master student. This is his thesis, and we worked on it together. And it deals with image recognition of figurative language. So figurative language is something that we all use, and some people describe a player in Twitter that left Chelsea. So they said that he jumped off the sinking ship just in time. And I don't really understand why, because I'm not really understanding soccer, but there is some meaning behind it, that he made a good decision to leave in time. So this is figurative speech, and like also it also relates to visual metaphors. And we compose a task that, for example, let the cat out of the bag, which is a phrase to its figurative meaning is to disclose a secret. And now we need to select the best image that fits to this phrase. So this is this image rather than the others. And blanket of snow, it's not the image of a blanket and not the image of the snowflake here, but something that really looks like more like a blanket of snow. So this is the IRFL work.
Can I ask the same question about the picture you just shown? Sorry. So I thought that taking the cat out of the bag had more to do with just disclosing a secret, but making it public knowledge, like letting everyone know that it's not a secret anymore. And here there's sharing a secret in a way that keeps it secret. So the question is again about this transition from text to images, and whether you transition from the figure of speech to a literal explanation of what it means, and then the connection to the pictures is straightforward, or whether the disambiguation or understanding what it means is directly into the picture.
And here we as well, like we let the humans, like the human majority, to resolve this a very correct like concern.
But you are the ones who chose the pictures, right? Or the expression, and somewhere you're doing the work that confuses me, I guess.
Yeah, so we have like an automatic generation, which we take like data sets of textual, figurative speech, and then we search like images that might be figurative in relations and might not. And then we let like the humans to like mark whether this is a figurative image or whether this is a literal image. So if we had like an image of a cat here, it would be literal, or a cat or a bag.
Okay.
And then we compose like the task, and we let humans like to solve it again. And while we when we have like a good human performance on the final data set, so we know that, okay, this is a data set that is like safe to use, and now we can test models on it. So it is true for all of the tasks that we compose.
Okay, thanks.
By the way, I'm maybe thinking out loud, but I guess if you have multiple defining a sentence, it's even stronger than. So I'm continuing what Aviv said, which is, this is not specific what I think it means. It's not in the same field. So multiple people would think like multiple pictures be connected to this sentence, right? And then you get a better representation of the embedding vector that you want to achieve. I'm just thinking out loud. I'm not sure that's true.
I'm not sure I understood.
Yeah, I'm basically asking, is it discrete? Like, do you have one sentence leading to one photo, or you have multiple photos describing the sentence?
Yeah. For each phrase, we have several images that are figurative for this sentence, and several images that are literal for this sentence. And there are also cases where it is both figurative and literal. So we have like all options. But finally, we compose tasks, and our like sanity checks is like to make sure that humans like solve it with high accuracy.
So if Aviv playing the game, he will see different photos than I'll see, basically.
You have access to the data set, and by the way, I can go into the website and show it now.
It's okay.
And Why doesn't because I'm in full screen. So you can just like go over like several like all of the tasks here, and you can select like idioms, similes, metaphors. So if you will both go over all of the data set, you will see like all of the instances as well. Okay, homework is a brief. So this is this one, and here is a fox. So this is not a fox. What is the answer here?
It
I
could
guess
be
the
the fox, but yeah, I
right
think
one?
the last one, no?
Probably the right one, yeah.
The right one.
The rightmost one, yeah.
Okay, great. So I'm coming back here. So in each of these data sets, we evaluated state-of-the-art vision and language models. And for completeness, with ablation tests and partial inputs, where we test like if the model receives both the text and the image, then we try like to have random text and or maybe to have like random pixels to make like sanity tests and several. And we also tried heuristics like to translate the image into text and to solve it. But the bottom line of all of this work is that they are easy for humans and challenging for models. And here we can see like on all like 5 works here of content sets, analogies, associations, we have the best model and we have the model performance and we have the human performance. And we still see like a big gaps and performance differences between the humans and the models. Okay, so this covers, and yeah, we will discuss whoops in a few slides. So this covers like the part of pushing the boundaries with challenging data sets. And so far, do you have any questions?
Did you consider anything related to gender bias?
To gender bias specifically, no. No, but like, actually, like I thought on the part of bias. I will show something that I think that relates to bias soon. I think it's even it's actually the next work. So like I think that gender bias is one case that you learn something through the data, but then you don't know how to generalize when you see a new instance. You like rely too much on what you've seen during the training, although the training is imbalanced as well. So in this case, if you see like a sentence, so this work, data efficient math language modeling, deals with math language modeling in vision and language. And this work is from NLP 21. And in math language modeling in vision and language, similarly to math language modeling in NLP, we have a sentence with the mask token, but now we have an image and we need to complete the mask token, but we look on the image in order to complete it. So if we see the sentence, a mask is eating the carrot, if we're given this image, we should say rabbit, and if we're given this image, we should say tiger. And like there is a variant of this work exactly that deals with gender and race. So you can like extrapolate on like a cleaning mask and then to see what the model will complete. And so this is MLM in vision and language. And when we looked on this task, we understood that in vision and language specifically, in many cases, no token was masked. And this is because captions in vision and language, unlike like paragraphs or Wikipedia paragraphs in BERT, are shorter. So the objective that was just exactly like BERT, 15% probability to mask a token, caused that in many cases no token was masked. But more surprising for us is that 50% of the tokens in the pre-trained data are stop words or punctuation marks. So let's look on this sentence. A mask is eating the carrot. We have 1, 2, 3 stop words, and we have like 4, 1, 2, 3 not stop words, like content words. So if we just mask randomly 50%, in 50% of the cases, we will get to masking stop word or punctuation, and we do not need the image in order to complete if. Yeah, we don't need a tiger mask eating the carrot. We don't need the image in order to complete it, and this is a pretty easy task to perform. So it led us to the understanding that the image is underutilized during pre-training. And the way we analyzed it is that we asked, how can we know which tokens will make the model actively rely on the image? So we asked this question, and we took an image, and then we made a prediction of the MLM with and without the image. So we took the sentence, a person performs a stunt jump on a mask, and we iterated all of the tokens and for all of the images, and we made the predictions with and without the image. And we see that with the image, we have like motorcycle, bike, ramp, bicycle, cycle, and without the image, we just have like random words, building, wall, beach, because the model doesn't know like what to complete here. And we then took the loss with the image and without the image, and we calculated the delta in this loss. And using this delta image loss, we knew which kind of tokens are the most significant in respect to the image. And then we created new masking objectives. Instead of randomly masking 15%, we created other masking strategies. So we have the baseline MLM here in this line, and in the x-axis is the amount of the pre-training data we experimented with, and in the y-axis there is the accuracy, and there is a strategy of content words. This is like the complement of stop words or punctuation marks, and we have masking objects, for example, like just tiger and rabbit and stuff that you can see in the image, and also to mask concrete words. And you can see that we made the model. We can see the published LXMER predictions and with the prompt of a photo of a. And the published LXMER says bathroom, beach, city, kitchen, woman, and like part is correct, but the model that was trained with masking objects know, not surprising, to complete like the objects much better. And so here we can see the graph of like just a photo image classification using our masking strategies, and the published LXMER is here and our masking strategies are here. And going back to the Wasser model, so we talked about word to vec, and here we took like just the same as word embedding, we took visual embeddings and composed b plus a prime minus a, like composed a new vector, and then we found which image, like which candidate has the is the most similar to this like arithmetic representation. So this is the model we composed for the Wasser work. And okay, now and there is another work that I just added today because this is a very recent work, and actually it's on not on vision and language, and I'm wondering whether it was smart to put it here, but I will go over it. No, you know what? I will skip it. I will skip it. Okay. So in all of this work, we try to improve the model. So our approach is inoculation by fine-tuning, which is basically just fine-tuning on the data sets that we like, on the train splits of the data sets that we have. And bottom line is that we see the training helps. So in all of these works, we have the model and we have the performance gain. And in the performance gain, we measure the best zero-shot model versus the best fine-tuned model. And the analogy was the most challenging, like, to improve, but also in the control sets and Winogaville and the other works, we did manage to improve it. So it also shows that the curated data sets serve as beneficial training signal. So we generated data sets with automatic methods, and one way to, if you train on it, you can improve on the test that is annotated from the generated data.
Yes, that's a question. You're training on a data set and then testing on the same data set. So why wouldn't it improve?
Yeah, so for example, in Wasser, we had the test set, the labels in the test set are of human annotators. But we created a data set in some automatic way, and we have some kind of automatic labels, which are different from what the labels that humans have selected. But there is something like between 79% similarity in the labels. So, but we did try to fine tune on the silver data, and we weren't sure that it will work, and it doesn't work perfect.
So you train on synthetic data that was created automatically, and you test on data set created by humans. Okay, now I get it.
Yeah, and in some ways we did train on the data sets that were created by humans as well. But improvement without extensive training is often the ideal case. So we do want, we hope that all of these data sets, and we say it in each paper, they should be used as test sets. This is like the best use that we see for it. Because Melanie Mitchell is an author in AI, and I agree with what she says, that it makes little sense to have extensively trained on each new example of abstraction or analogy, because these are stuff that we as humans just know to extrapolate and to understand without like extensive training for each new task. So this is the ideal case that we see, and we hope that the community will reach there soon. Okay, so now let's discuss groups. So what makes these images? By the way, how long do we have, Rachel?
We have an hour and a half, but you don't have to speak all the hour and a half. Usually we have like between half an hour and an hour of a lecture, and then some discussion.
Okay, cool. We saw some images before, and now there are other ones. So, okay, what about this one? Why is it weird?
He has an iPhone, and it doesn't exist back then.
Okay, yeah, okay. In this one?
It's still
no oxygen.
What? I didn't hear you.
The fire should be out because there's no oxygen inside.
Yeah, correct. Yeah, so this is more challenging, and this wolf should usually house during the night and not during the day. So yeah, so we did see some examples before, and these images exist in the wild as well. And these kind of images also always like intrigue our curiosity and makes us wonder and understand why it is weird, and sometimes make us also laugh. So this image became famous during the last World Cup, where Messi and Ronaldo played chess, and it makes people intrigued because their competition usually happens on the on the soccer field and not in a game of chess. And in here we can see a fire displayed on the monitor in a fireplace instead having a real fire. And here there are can of Coke inside a plastic bag. So these are weird images. And the fun fact is that GPT-4 was released in the same day as Whoops. And it also had cases of what is unusual about this image and what is funny about this image. So we were happy that we made a data set that is similar in nature to these tasks. So we had human to generate synthetic images with text-to-image models. So we recruited designers, image designers that use text-to-image models like Midjourney, and they were instructed to generate common sense defined images. And they were recruited through social media, and they are just people that are not like technical workers and not researchers and not related to NLP or computer vision. And how to create weird image. So they were instructed to think about an image that depicts two elements, X and Y, that are likely to co-occur. For example, the guitarist Slash plays on a guitar, right? So now we can replace Y with a different element, Y prime, that is unlikely to exist in reality. So here we replace the guitar with a saxophone. And this is how we receive like weird images with Midjourney. And this way we created of diverse nature and reason of what makes them strange. And we analyzed and categorized the reasons. And we have several categories, for example, atypical behavior, and this is like a cat that is jumping to a tennis ball like dogs do. And this is object shape. This is a glove with 6 fingers. And age mismatch and safety and cultural knowledge. These are little girls crying in Disneyland and so on. So we have a large diversity of images with reasons of what makes them weird. And now we want to see whether models understand this type of images and also the like explaining what makes it weird, but also other types of understanding. So we used Whoops to create vision and language tasks. And the first task is explanation generation. And here we have the weird image of a panda catching a salmon fish in the river like a grizzly bears do. And the explanation of what makes it weird is that panda live in China bamboo forest, subsist almost entirely on bamboo, and do not hunt salmon fish like the grizzly bears. And so this is like the novel task of explanation generation, but we also had other tasks of image captioning and to describe what happens in the image, and cross-modal matching, where a model, like a model that has scores like CLIP, needs to provide a higher score for a panda bear is fishing for a salmon rather than just a bear fishing for a salmon, which both captions are true, but this caption is underspecified. And also VQA, what is catching salmon in the stream? Panda. And what does panda bear trying to catch? Salmon. And this task, our motivation for this task is to see whether the model is confused to say this is just a bear or this is a grizzly bear, or to say that maybe it is a bamboo that the panda tries to catch, and to measure bias. So we composed many like these 4 tasks and annotated with humans more than 10,000 annotations. And now we want to evaluate models and to see how models deal with these tasks. Okay, so far, are there any questions about the weird images, their motivation, and our adaptations?
Yeah.
Yeah.
Although I have to apologize, it's always the same question, but here it's in a different form. But about the weird images, you started out from text, constructing, having the weird idea in text, turning it into an image, then trying to figure out what was weird about it in things. So I'm trying to see why there is something rather than just, you know, for example, captioning the picture, which is like a standard visual NLP task, and then just telling about the text, why this text represents something weird. What's unique about transitioning to the visual medium?
Yeah, so you ask, okay, you say that one way to solve this task is to translate this image into text and then to ask about the text. And yeah, this is something that we did, and we will show this approach. But like, I will hint what is the final answer is that this translation, there are many ways to translate what happens in the image, and not always it will represent the weird aspect. Like, for example, the first thing that comes to mind in this one, no captioning model will say that this is a sealed bottle, a sealed jar with a lit candle in it. They will say something like, oh yeah, there is a candle in a jar. And if you will think of a candle in a jar, there isn't something strange in it. Yeah, so this is the kind of like problems that happened with the incomplete captions, and it stems from the fact that captioning models do not always know how to identify, but also that they present something that is sometimes incomplete, and you may need like many different captions of different areas to describe it. And we will see this method in the experiments. So yeah, so we developed two approaches for solving it. The first is an end-to-end approach, where we take model like Blip2, which is a vision and language model completely, and we asked it what makes this image weird, and who knows Blip2 can know that like they had in their paper cases that are similar to this kind of prompts. So if you look on their paper, you might think that this model is good enough to solve whoops, but we will show that this model didn't succeed at all. So it produced, like in this case, it produces the wolf is howling at the sun, which actually this was correct. And and we also fine-tune this model, and which says wolf usually howls during the night and not the day. Yeah, I take it back. The wolf is howling at the sun. This is the caption. This is not an explanation of what makes it weird. So this is not correct. And we also have a pipeline approach. And in the pipeline approach is just as you said, Aviv, that we have a predicted caption of wolf howling at the top of the rock at sunset, and then we ask GPT-3. This was the available model then. What makes it weird? And it says a wolf howling at the top of a sunset. It is not a typical behavior of a wild wolf. But if we give it like the ground truth caption, and this model is an Oracle model, and and in this case we feed it with the human curated caption. So a wolf howling, a bright sunny day background, and in this case the model says that a wolf typically most active during the night and not the day. So this is better. So we took this task of what makes it weird, and we split it to two. We also have like to identify whether the image is weird or not. So here we had images that are not weird. So we had Albert Einstein holding a notebook and not a smartphone, and we had a wolf that is howling at the night and not the day. And we then let the models to identify, and this is a random chance of like 50-50. And also for the explanation task, and this metric is human rating. And first, we see that if we look on the end-to-end model, the zero-shot blip2 achieved 0% in this task, actually. Because the zero-shot model always provided the caption and not the explanation. But the fine-tune model achieved 27%, which is higher, but still not very impressive. And the pipeline approach with GPT-3 all actually performed better, and it reaches 33%, but it is still very far from the human performance at 95%. And even the Oracle model, which received the ground truth caption, a caption that exactly says, like depicts the image, including the stuff that make it weird. Like, for example, in the case with the seal jar and the lead candle, it will specify that this is a seal jar and this is a sealed candle that is lit inside the seal jar. And the performance was not good as humans as well.
Which GPT-3 is that? Because they improved a lot on that.
It's the last one.
For the humans here, are they given? Did you, by any chance, give them both the image, right?
Yeah.
I wonder if the humans would do differently if they get the caption and not the image.
Yeah, I think that using the caption should be easier than the image, but I'm not sure. But
this is a question about humans and not about models.
Yeah. But the task that we wanted like to have is like the visual task, and we just transfer to text because this is a very legitimate way and a good way to solve. But for us, it's very easy, like to see, identify it, like the Ronaldo example and like the fireplace example, and to immediately understand, okay, there is something weird, and let's understand real quick what is weird here, and share it in Twitter. And here we can see some of the fine-tuned blip predictions, which is not bad. And the Statue of Liberty is in New York, not Sydney. And this is an image with both the Sydney structure here and the Statue of Liberty. And babies are too young to read books. And the Cookie Monster eats cookies, not apples. So these are some predictions of the fine-tuned model. And we had an analysis, and we asked, okay, we generate images with Midjourney, and it could be that the challenge of models stems from the fact that the images are generated and not because they are real. So we took the strange images, the weird images, and we also generated normal images. They are the same image, but do not contain the weird aspect. So if this image is a person with ice skates on like parquet, in this case, the ice skates are really on ice. And in addition to the normal images, which are synthetic as well, we had natural images. And the natural images are like real images that were taken with photographs. And then we measured the model performance on each cases. And we saw that the model succeeds on the natural and normal categories high. And by the way, equal accuracy of 89%. But the challenge and the struggle is specifically on the weird category of 49%. So this led us to the understanding that the main challenge is the weirdness and not the synthesis of the images. So this concludes Whoops, and you're welcome to check out the project website, and there is the dataset available in Hugging Face, and there is evaluation collab for evaluating models, and the full explorer to iterate over all of the images and see all of the human annotations. And yeah, I didn't say it, but we have 5 different humans annotate each image. So there are both the captions, and the explanation of what makes it weird, written by 5 humans, and this was a very fun project. Okay, any questions about Whoops? Okay, cool. Now regarding like follow-ups and future works, so we also asked how to select beneficial multi-modal data, and there is a work, it's called DataComp. It was actually published 2 days ago, and for multiple dataset construction, and how to develop a scaled open source vision and language model. And this is a work of OpenFlamingo, an open source version of the Flamingo paper by DeepMind. And both of these works are with collaborators from University of Washington and AI2. And there are some other works, for example, in spotting bottlenecks in multimodal data beyond vision and language. And this includes working with the video modality, or that also contains audio. But I want to briefly present a work that we should publish pretty soon on how to leverage LLMs to improve text and image alignment. And it's called What You See is What You Read on Improving Text and Image Alignment Evaluation. So what you see is what you read. This is a question, and we have a text. The dog is resting on the chair on the porch of the house, and there is an image. And we understand that the text does not align with the image. So this is the task, because this is a cat and not a dog. And to test it, we constructed C2. And C2 is a comprehensive evaluation set. And by the way, this is the work with Google. So C2 is a comprehensive evaluation set, and we have both real text and real images, and also all cases of like synthetic text and synthetic images as well. So we have like all of the combinations, and we construct a comprehensive evaluation set with 3,200 images. All are human annotated. And we create 2 methods. The first is called VQ squared, and this is a zero-shot method. And in this method, we have the caption, and from the caption, we generate questions and answers. So the caption is the dog is resting on the chair on the top of the house, and we generate the question, who is resting on the chair on the porch? And the answer from the text is a dog. And then we take like a VQA model, a model that also have an access to the image, and we ask it to score whether this answer is correct. And in this case, it will say that it will rank a low score for the dog because it sees that this is a cat and not a dog. And another approach is a fine-tuning approach, where we just fine-tune over the data sets that we create and construct. And I just iterate the results very quickly, is that both methods surpass prior approaches in various text and image alignment tests. And it happens especially for cases with synthetic images. So here we have many model baselines, Clip and Coca and Bleep and Bleep2. These are all like state-of-the-art models. You all know Clip. Bleep2 is also a very good model. And there is Poly by Google, and there is Tifa that was published very recently. And this is the VQ squared method. And it achieves a robust improvement over all of the data sets, and especially in the cases with synthetic images here in this line. And we also achieve state-of-the-art results on the Winogrand task, which we show in the paper. And we show that we can localize specific misalignment, and to say like that the problem in this caption is the dog part, like to say what is contradicting. And this method also allows us to compare text to image models and to see like which model produce images that are better aligned with the text. And we also plan to improve this kind of models as well. Yeah, so we plan to use it as a automatic score in text-to-image generation. Yeah, so this is the last work, and all of this work in this presentation were conducted with many awesome collaborators, which I'm grateful to have, and my supervisors, Gabriel Stanovsky and Roy Schwartz, and that's it. Let's talk about the takeaways. Is that multimodal reasoning is crucial for real-world applications, and we encourage to explore novel methods and challenging tasks to expand the current boundaries. High-quality data sets enable better AI, and synthetic data generation, leveraging semantic inputs, LLMs, and text-to-image models is key to building such data sets. And happy to talk about data generation, new vision and language benchmarks, automatic evaluation metrics, synthetic images, and more. Thank you very much.
תודה רבה, יונתן. שאלות?
יונתן, סופר מעניין, אגב, ותודה שהצגת לנו וכדומה. סתם שאלה שכאילו, אני אשמח לשאול, דברים כמו hallucinations שקורים ב-language models, זה קורה גם ב-image to text או text to image? נגיד אתה מג'נרט תמונות על בסיס הדבר הזה, אתה גם תראה שם hallucinations?
כן, חד משמעית זה קורה. אז למשל, כאילו חלק מהבעיות ב-text to image model זה שאתה תכתוב, נגיד, אתה רוצה, לא יודע מה, כלב לברדור עם כובע בצבע סגול, כובע עם 3 פינות, והוא יכול לעשות לך או כובע בצבע אחר, או כובע עם 4 פינות, או משהו כאילו זה, אפשר לקרוא לזה סוג של הלוזינציה. יש גם בכיוון ההפוך, שאתה מבקש קפשן לתמונה, ואתה או שלא מקבל את כל הפרטים, או שמקבל באמת פרטים לא נכונים. זה גם סוג של הלוזינציה. זה גם קורה עכשיו, יש עבודה חדשה בשם Image to Para, שהיא ממש מג'נרטת פרגרף שלם, כאילו עם ChatGPT וזה, על כל הדברים שיש בתמונה, כאילו על האובייקטים ועל היחסים ביניהם, ואם מנסים את זה על כמה דוגמאות, אתה רואה טעויות מאוד מאוד רציניות, שזה כבר יותר דומה להלוזינציות שמכירים מטקסט אונלי, כי זה ממש כבר נהיה פרגרף, ואז שם באמת השגיאות הן יותר משמעותיות, אתה יותר שם לב אליהן.
וכשאתה עובד עם image to text, אז יש לך עדיין שכבת סמפלינג כמו שאנחנו מכירים, או שאתה משתמש תמיד במשהו כמו גרידי או כדומה?
ב-image to text, אז כן, זה אותם רעיונות, כאילו חלק מהמודלים ממש אפילו משתמשים נגיד בליפ 2 משתמש בפלן T5 extra large, או פלן T5 כלשהו, גם extra large, או ב-OPT, כלומר בליפ 2 הוא נקרא לזה ממזג בין מודל שפה, שזה או OPT או פלן, לבין מודל ויז'ן, שזה ויט למשל, ועושה את זה מאוד איזשהו Q-former, שזה בעצם משהו שממזג ביניהם, וככה הוא בעצם מג'נרט את הטקסט. אז בסוף מה שמג'נרט את הטקסט זה אותו מודל שפה שאנחנו מכירים.
יש לי שאלה. כן. טוב. יש לי שאלה לגבי הנושא של eventual, כאילו דברים שקשורים דברים שהם time sequence, כאילו, בין אם זה סדרת אירועים או התמצאות במרחב, שהיא גם כן הבנה ספציאלית, אז עד כמה פשוט הצפה בכמויות דאטה גדולות יכולה לפצות על זה של החוסר בגראונדינג בצד של ה-eventual experience, eventual data. היה ברורה שלו?
יונתן איתנו? איבדנו את יונתן. טוב, עד שיונתן יחזור, אז אני אספר שבינתיים נודע לי שמותר לספר, שירדן טל גם ילדה, אז יש לנו הרבה בשורות טובות היום במועדון, לפני 4 ימים.
גם תאומים או שזה היה רגיל?
נראה לי שלא. למרות שזה היה נראה בוואטסאפ של, אני כבר דאגתי של יהיה תאומים, כי לכולם בוואטסאפ של הג'ורנל קלאב כן יש תאומים.
פתאום התחילו להגיע לכאן אימהות שפשוט לא תאומים, זה לא...
זה בקורלציה, הנה יונתן חזר.
קראתי המחשב, מזל שזה קרה בסוף ההרצאה ולא באמצע.
בסדר, בינתיים ריחלנו על כל מיני אנשים שילדו. כן, אז מי ששאל את השאלה יכול לחזור?
כן, אורי, אז נקטעת באמצע של השאלה?
שמעתי על טיים סיריאס ועל וידאו למשל ועל סיקוונשל.
כל הדברים שהגראונדינג שלנו מבוסס באמת על eventual perception, כאילו, בין אם זה ספיישל, או בין אם זה סדרת פעולות, או דברים מהסוג הזה, אז עד כמה הצפה בדאטה שהוא לא eventual במהות שלו, מצליח לפצות על זה, ועד כמה, ואיזה ניסיונות יש אולי בדרכים באסטרטגיות אחרות ללמד את ההיבטים הזמניים האלה.
כן. זה נקודה מצוינת. יש לי 2 דברים שקופצים לראש, אז אחד מהם זה עבודה שאנחנו משתפים פעולה עכשיו, שהיא עוסקת, זה לא בדיוק וידאו, אבל בואו נעשה את זה, קודם נדבר על משהו שהוא לא בדיוק וידאו, ואחרי זה גם נקפוץ לוידאו. אז בעצם הם מתעסקים בעצם בסוג של מתכונים. אז במתכונים יש לך חלק כזה, אתה רואה תמונה, נגיד, תשים את הבצל בסיר, תטגן אותו, ולא יודע, אז תוסיף פלפלים או משהו כזה. ואז בעצם אתה מקבל, אם לפני כן ראית רק בצל בסיר, אחרי זה אתה רואה בצל מטוגן, ואתה רואה שם גם פלפלים שהם לא מטוגנים למשל. אז יש כאן איזשהו temporal consistency שצריך בעצם לשמור עליה. אז חלק ממה שאפשר לעשות בעצם כדי להבין את זה, זה קודם כל להבין איך מודדים בעצם את הדברים האלה. אז מזה באמת אפשר ללכת לדאטה סטים של וידאוים למשל. הרי יש כל מיני דאטה סטים של וידאוים, למשל יש דאטה סט שנקרא Epic Kitchens, שאנשים שמו GoPro על הראש בזמן שהם היו במטבח וצילמו את כל התהליך שלהם. ואז אפשר כאילו לדגום כל מיני סגמנטים, ובתחילת הסגמנט ובסוף הסגמנט, שסגמנט זה למשל מציין את השלב מסוים בהכנת המתכון, ואז למדוד את הפריים, כאילו לראות מה קורה בפריים לפני, אחרי, ואז לעשות כל מיני הפרשים, גם הפרשים סימנטיים וגם הפרשים ברמת הפיקסלים, כדי להבין האם התמונות בעצם מייצגות את השלב לפני ואחרי. הרי כאילו, בעבודה שאני מתאר עם המתכונים, חלק מהבעיות זה שלמשל אתה מראה בהתחלה את הסיר עם הבצל לצורך העניין, ואחרי זה שאתה עובר לסצנה הבאה, בגלל שזה מודל שמייצר תמונה, אתה מקבל פתאום, לא יודע, מחבת שונה לגמרי, או פתאום זה סיר, או פתאום זה במטבח אחר וכאלה, ואז זה לא נראה בעצם טבעי. אז יש כאן איזשהו אתגר יחסית חדש מהבחינה הזאת. אז גם פה, כאילו, חלק גדול מההתמודדות זה בעצם קודם להבין איך מודדים את זה, ואחרי זה להבין איך משפרים את זה. עבודה שבעצם משפרת, יש עבודה שנקראת מרלו ריזרב, זו עבודה מ-University of Washington, והם בעצם לקחו את וידאוים, והם עשו כמו Masked Language Modeling, ועשו את זה עם פריימים, ובעצם חלק מהמשימה זה להבין האם פריים אחד הוא עוקב אחרי השני או לא. אז הם כאילו נתנו לייבל חיובי לפריים שהוא כן עוקב, לייבל שלילי לפריים שהוא randomly sample, וככה הם בעצם ימנו את המודל, והם ממש הראו שכאילו כל שלב כזה, הם עשו כל מיני objectives שקשורים גם לוידאו וגם לטמפורל understanding, וככה הם ימנו את המודל והראו שזה בעצם תורם. אז זאת העבודה שנקראת מרלו רזרב, למי שרוצה להסתכל.
תודה.
יש לי שאלה כזאת יותר כללית. בעצם הדאטה-סט נורא מגניב, אבל רוב התמונות בעולם הן כן תמונות הגיוניות, הן לא תמונות לא הגיוניות. אז האם בדקתם שהמודל שאימנתם להסביר למה תמונות לא הגיוניות, יכול לעשות ריזונינג גם על תמונות הגיוניות, או כאילו שהריזונינג שלו גם על תמונות הגיוניות משתפר. אחרת בעצם, מה עזרנו בזה לעולם האמיתי?
כן. אז דבר ראשון, כן עשינו בחינה בעצם, כן עשינו את המשימה גם של האם זה מוזר או לא מוזר, וכאילו אפשר, אז אפשר, בוא נגיד ככה, אם ניתן תמונה רגילה למודל שאומר למה זה מוזר, יכול להיות שהוא ימציא משהו שהוא מוזר כי זה מה שהוא יודע לעשות, אבל אם כאילו משרשרים את זה, ואומרים קודם תגיד אם זה מוזר או לא, אחרי זה תגיד למה זה מוזר, כאילו אפשר גם לעשות משימה כזאת אחת מאוחדת, אבל בעצם את כאילו נראה לי שיותר רוצה לשאול על מה קורה בהבנה על תמונות אמיתיות, נכון?
כן, בדיוק. אם יש, נגיד יש תמונה אמיתית שעדיין צריך בריזונינג לא טריוויאלי. לא יודעת, להבין שבן אדם עובד על מישהו אחר, מי שמכיר פה את דני ידעני, אז יש לו תמונות כאלה, להבין מי הרוצח מהתמונה וכל מיני כאלה.
כן, אז דבר ראשון, אני כאילו ממש אוהב כאילו משימות כאלה, ואנחנו כאילו, גם אני וגם השותפים שלי תמיד מנסים לחשוב, אז אם יש למישהו רעיונות על כאילו איזה תמונות יכולות לתאר ריזונינג שהוא לא טריוויאלי, אני באמת מאוד אשמח לעבוד על זה. מה שיש, כאילו נקרא לזה, מה שיש בשוק עכשיו, הרבה מאוד זה כאילו פשוט קפשנינג, ולתאר מה קורה בתמונה, ולתאר את האובייקטים, לתאר את היחסים בין האובייקטים, איפה ממוקם כל דבר, על ריזונינג, זה כרגע כאילו פחות יש, אני כן צופה שהולך להיות יותר ויותר, ואנחנו כן עובדים גם על דברים כאלה, אני כן עובד עם החבר'ה מוושינגטון, כן עובדים על כל מיני דברים כאלה, למשל לקחת תרגיל בחדווה, או תרגיל משוואה ריבועית או משהו כזה, לכתוב אותה על דף, עם דף ועט, ואז בעצם להגיד למודל תפתור. כאילו, אז הוא גם צריך לקרוא את זה, לראות את התמונה, להמיר את זה לטקסט, ואז לבצע את הריזונינג, או כל מיני, זו דוגמה אחת. יש לי עוד דוגמאות.
יש קריקטורות, נגיד, כן? לקחת קריקטורה ולשאול מה מצחיק פה. יש המון קריקטורות.
אז כן, קריקטורות יש עבודה כזאת, אלקטריק צ'יפ, משהו כזה זה נקרא, של ג'ק הסל, שהוא גם שותף בוופס, אז זה באמת כאילו, זה בדיוק העניין הזה, לקחו קטגוריות מניו יורק משהו, ובדיוק צריך להסביר את מה מצחיק בעצם. כן.
לי שאלה, כאילו מעבר לניסיון של לייצר דאטה סטים או לעשות מניפולציות של המשימות עצמן, אז יש עוד שיטות לשפר את הנושא של common sense reasoning, כמו שילוב כזה של word knowledge, או כאילו קישור לדאטאבייסים כדי שהמודלים ידעו איך לג'נרט תמונות או הפוך?
אפשר לחדד יותר את השאלה?
אם אתה מכיר או יודע שגם כאילו במודלים כאלה של vision יש עוד שיטות אחרות לנסות לשפר את העניין הזה של common sense reasoning, אז דוגמה אחת זה שילוב של knowledge bases כאלה, עם word knowledge כזה, שמעבר לדוגמאות שבאות לידי ביטוי בדאטה סט.
כן, שאלה מצוינת. אז בוא נגיד שהתחלתי לעבוד על התחום, כאילו בכללי זה גם היה קטע כזה עם מודלי ויז'ן, הם כולם היו בקטע של כאילו אימג'נט, בוא נעשה מודל שפותר בעוד 1% על אימג'נט, כן? זה היה כאילו איזשהו פער, לפחות אני הרגשתי, גם בחיבור עם real world וגם בחיבור כאילו עם common sense, ובגלל זה גם עניין אותי לחקור את התחום הזה. מאז יש למשל מודל, יש כאילו משימה שנקראת OKVQA, יש כאילו VQA רגיל שזה visual question answering, שצריך להגיד מה מופיע בתמונה או באיזה צבע הכלב וכל מיני דברים כאלה, אבל יש ממש משימות שדורשות הבנה, או OK זה knowledge, שכחתי מה O אומר, אבל זה כאילו knowledge חיצוני בקיצור. אז למשל יש שם משימה של באיזה מדינה מופיע הבניין הזה, ורואים את התמונה של הביג בן, ואז כאילו אנחנו יודעים שזה באנגליה. נראה שהכיוון שזה הולך כרגע, זה יותר ויותר לבוא, למזג בעצם מודל תמונה, שיודע לקחת את התמונה, להוריד אותה לאיזשהו וקטור מאוד דנס, ואז לבוא למודל שפה ופשוט למזג את האינפורמציה הזאת עם המודל שפה, כי המודל שפה ידע להגיד בעצם כאילו שהביג בן נמצא באנגליה, וכאילו את כל ההיסטוריה שלו גם, ומי בנה אותו, ועוד מלא פרטים שאנחנו לא יודעים, אבל המודלים יודעים הרבה יותר מהר וטוב מאיתנו. איזה עוד עבודות שמתמזגות עם מקורות מידע חיצוניים? אז היה גם כל מיני עבודות, גם ב-NLP, שבעצם לפני המודלים הגדולים שהתאמו על הרבה דאטה, שפשוט לקחו גרפים. למשל, בנו גרפים, יש גרפים למשל שנקרא קונספט-נט, יש גרף כזה. קונספט-נט זה כאילו גרף של מלא קונספטים, שכלב זה יונק, ויונקים, יש שם גם את חתולים, ויש שם טיגריסים, וטיגריס הוא קרוב משפחה ממשפחת חתולים, וכל מיני עצים כאלה, שגם קשורים ל-NLTK, ובעצם נתנו למודל להתאמן, ובעצם להסתכל על הדאטה הזה, ולעשות attend כל פעם לנוד הרלוונטי, וכל מיני דברים כאלה, אבל מה שהולך עכשיו זה יותר ויותר פשוט מודל שפה גדול, זה יותר הכיוון שזה הולך אליו גם בוויז'ן וגם מחוץ לוויז'ן, ואני חושב שלאור ההצלחה זה מה שיותר נראה בעתיד גם.
אז תודה רבה יונתן, נראה לי שנסיים פה כי כבר נהיה מאוחר, היה מרתק ממש ועבודה מדהימה, ותודה שבאת לספר לנו.
שמחה, תודה רבה לכולם על ההשתתפות. אוקיי, תודה. יום טוב.
ביי, תודה יונתן. ביי ביי לכולם.
תודה.
תודה.
לילה טוב. תודה.